I'm Gabriel Kaptchuk. I'm a PhD student at Johns Hopkins. This is a work that we did with myself and two other, at the time, grad students, Arka and Ian Myers, as well as two professors, Matt Green and Abhishek Jain. It's entitled Fairness in an Unfair World, Fair Multi-Party Computation from Public Bulletin Boards. So without any further ado, we're kind of going to be talking and do sort of the basic introduction to MPC. If you've gone to the other MPC session today, I apologize in advance. But MPC is a primitive in which if we have multiple parties, each with a private input, x1 through, in this case, x4, but through a general xn, they want to compute some function f over their private inputs and get the output y. And they want to be able to do that without revealing each of their private inputs to the other parties. And this is equivalent to the ideal world case where we have some external trusted party that takes in everybody's inputs, computes the function f, and then returns the output y to all of the parties. And so this is the ideal world situation, and it's been shown in general that we have constructions which are secure against adversarial players. Unfortunately, it might be secure against those adversarial parties, but we don't necessarily get all the properties that we might want from this protocol. So for example, if imagine our MPC protocol that we're running is an auction, each player puts in a bid, and the output is the winning player and the amount that they have to pay. In the last round of that protocol, in most known MPC constructions, for general problems, all MPC constructions, some player has to move last, and that player needs to send the output of that function to another player. If that first player who's sending that final value is adversarial, they can, instead of sending the actual output of the function, they can send the special abort symbol, meaning that there's a network failure, or in this case, that they didn't actually want to share that result. What that means is that an adversarial party can get access to the output before any other player. In the case of an auction, this is a really, really big deal, right? If an adversarial player didn't win the auction, and they actually now know that they didn't win the auction, and they know the exact amount they might have to bid in a rerun in order to win the auction, right? So an adversarial party can gain a huge, huge advantage from doing this. What we really kind of want is an implementation of MPC in which either all players get the output or no players get the output, right? And this is referred to as fair multi-party computation. This is referred to as fair multi-party computation and has been studied for quite a while. This is a sort of very high-level number of citations for the extreme amount of work that has gone into fair MPC. The first and sort of most important result is general fairness is known to be impossible without an honest majority. And this was shown in 1986. And then once that was known, a lot of work went into different types of fairness, right? So instead of trying to achieve this ideal notion where either all players get the output or no players get the output, they instead tried to achieve something along the idea of different types of fairness. So one such example is a gradual release mechanism where the various players, instead of simply sending each other the entire output in the last step, would exchange bit by bit the output. And so if at any point in time an adversary did abort, only some of the final output would be known by the adversarial party and not by the honest party. Later in 2008, it was shown that for restricted classes of functions, we actually can get true fairness, but there's still a large number of those of desired functions that we couldn't implement with real fairness. More recently, this problem has sort of resurfaced using two basic different primitives. One is fairness with penalties, which I'll talk about a little bit more in the next slide, and most recently, delta T fairness with trusted hardware. Delta T fairness is basically a new kind of gradual release mechanism in which instead of trying to measure the number of bits that an honest party might not be able to receive, it's instead an amount of computational time that they would need to receive. So a little bit more about fairness with penalties. We're spending some time here because in many ways, on a surface level, the work on fairness with penalties looks most familiar or most similar to our work. But honestly, if you sort of delve a little bit deeper into it, there are a lot of really important differences. So the basic way that fairness with penalties works is that each player puts some amount of money into escrow, and that money is forfeit if an abort happens during the protocol, right? So if some adversarial party aborts, all the money that they put up before the protocol execution goes to the honest parties. In general, we use blockchains as payment channels, but sort of any decentralized currency would work well here. There's two major problems with fairness with penalties. First of all, it requires each party to have a sufficient amount of liquid capital to actually put in to the computation, right? So if two different parties are trying to do some computation, that the assets with which they're doing that computation are really valuable, they might not have the raw cash to put into the escrow, right? So it's not always possible to even do this. Sort of at a more fundamental level, this isn't really fairness. What it basically is it allows an adversary to buy out of the fairness property once they see the output of the function. And that's a really important piece of information because it sort of builds a cyclical dependency, right? So the amount of money that the adversary might be willing to pay in order to buy out of fairness is actually a function of the output of the MPC function, right? So now, in order to determine how much money needs to go into escrow, you actually need to know something about the output of the function, right? So we get this weird cyclical dependency, which basically forces everybody to put up way, way, way too much money in order to get any fairness at all. So in our work, we're going to sort of move away from these sort of weaker notions of different types of fairness and work to achieve true fairness. And we're going to do that by introducing public bulletin boards. Public bulletin boards are basically the digital equivalent of the same thing that you might see walking around a college campus, but we're going to sort of enumerate their properties a little bit. The first of those properties is that messages are permanently available, right? So once a message goes up on a public bulletin board, it's never coming down. This is generally true of the physical representations as well, but we need this to be sort of a digitally ensured property. Secondly, we need messages to be visible to all parties, right? This is the public part of public bulletin boards. All players need to have some method of communication with the bulletin board directly. And lastly, the bulletin board needs to produce a proof that some message is actually on the bulletin board, right? That the message was posted publicly. In general, you can think about this as a signature, right? So once a bulletin board receives a message, it's going to sign it with its private key, and then the tuple of the message and that signature is going to prove that it is indeed publicly available. So why on earth are we using bulletin boards? So I think the main reason here is that bulletin boards are not some weird abstract concept. Bulletin boards exist in reality all the time. And in fact, many existing technologies are practical implementations of bulletin boards. The first example of this is blockchains, particularly Bitcoin, Ethereum as examples. And instead of using a traditional signature, they use confirmation blocks as signatures, right? Once a certain number of confirmation blocks have been appended to the chain after the transaction in question, we consider that that message to be immutable. It's part of the blockchain forever. And because of the decentralized nature of the blockchain, everybody has access to it. So that's that public piece. Another technology which you can use is certificate transparency, which is a newer technology that basically holds certificate authorities accountable for what they're doing. Each time they issue a new certificate, it gets appended to the certificate transparency log where everybody can see it, and the presence on the log is guaranteed by a real digital signature. Another really great piece of bulletin boards is that we don't actually need to trust bulletin boards to do more than just their basic job. We don't have to fiddle with them in order to get fair multi-party computation out of them, and they don't even have to know that they're being used for fair MPC. So let's start to build up some intuition as to how we're going to get fair MPC from normal MPC plus blockchain plus bulletin boards. So imagine we've got two parties in this case. They define some MPC circuit between the two of them. They can send in their inputs. And what we would really like to happen next, and we could sort of solve the problem immediately if we had this, is that we want the MPC circuit itself to send the output directly to the bulletin board, right? If the bulletin board is able to have that output, now all players could simply go to the bulletin board immediately and get the output, and there'd be no way for an adversarial party to interfere with an honest party's ability to get that function output. Obviously, this doesn't work because there is no trusted path between the MPC circuit output and the bulletin board, right? So we need to build something a little bit more complicated here. So now we're going to sort of complicate it a little bit and build towards our actual protocol. So once again, we take in the inputs of each player, but instead of just the normal function output, what we're going to output is an encryption of the output, right? So now this is the encryption of Y, and each player is going to get the encryption, and now everybody gets sort of this ciphertext, and it's sort of meaningless to everybody because we haven't really talked about keys, right? But this is sort of, if everybody were able to get a ciphertext, then maybe we could build some kind of mechanism whereby once everybody has a ciphertext, everybody can open that ciphertext, but not before everybody has it. So we're going to call that primitive basically conditional release. And what conditional release is it's an encryption mechanism in which the key to that encryption scheme is a proof of public availability of the ciphertext itself, right? So once a message goes up on a bulletin board, the presence on the bulletin board is actually going to function as the key to that encryption scheme. And we're going to build that with witness encryption and with trusted hardware. Witness encryption being a sort of more theoretical result, and trusted hardware being a more practical oriented result. So what does our actual protocol look like? Once again, we have these two parties. They're going to compute some function and get the encrypted output. Then any player, doesn't matter whether adversarial or not, can take that encrypted output and post it directly onto the bulletin board. Once the bulletin board has it and has signed it or has accepted it as a message, it really functions as the key to this encryption scheme. And then each player can go onto the bulletin board, pull down that effective key, and now they've got the key and the ciphertext, and voila, they have the output, right? So this is going to work basically because we need the public part of the bulletin board to ensure that everybody can get it before anybody can actually look at the function output. So delving a little bit more into the theoretical part, the theoretical result, we're going to use witness encryption in order to build conditional release. For those of you who are not familiar with witness encryption, we're actually using a specific form of witness encryption called extractable witness encryption. But the idea here is that you can take some message M and encrypt it under a statement X in some language, right? And that if a adversarial party doesn't have a witness to the statement in that language, then they can't distinguish between ciphertexts and they can't decrypt the message. But if, on the other hand, somebody does have the witness, they can decrypt the function and look at the message, right? So what's really nice about this is now we basically have the conditional release mechanism that we wanted before, right? We can use this witness to a statement to as our proof of public availability. So how does this work when actually running the protocol? We have some number of players, they send in their inputs, and each of them receive as output the encryption of the function computation, right? And this is not just a normal encryption, this is going to be a witness encryption, and it's going to be a witness encryption under the statement, this ciphertext bears a valid signature from a bulletin board, right? Then a player can take the ciphertext or the witness encryption ciphertext, post it onto the bulletin board, at which point it will get a signature, right? And as we said before, the encrypted the statement under which we're encrypting is basically this signature plus this ciphertext. So now everybody can go and retrieve that as the key to their functionality. Now this would be really nice, except once again, we've kind of introduced a circular dependency here. And this is that we can't use the ciphertext itself in the statement, right? Because then we'd be using the ciphertext as part of the encryption of itself. So trivially, this isn't going to work. So what we do instead is instead of using the actual ciphertext on the bulletin board, what we're going to use is a release token. And this release token is going to be an output of each player's private input into the MPC, right? So you can imagine each of them generating a random share of it, putting that random share into the MPC circuit, and then as each one of them actually receives the witness encryption, they can go and say, hey, I have the witness encryption, here's my share of the key, or of the release token. Once they get all of the release tokens, they can post them onto the chain and proceed as the animation just did before, right? Now, unfortunately, witness encryption is not the most practical of things, and so we wanted to also build a sort of practical implementation that could be run today. And there's a number of building blocks that we're going to use in order to make that a reality. The first one is going to be trusted hardware. In our specific application, we're using Intel SGX. For those of you who don't know SGX, SGX is basically an environment for code to be executed which can be considered trusted. It's hardened against even an adversarial operator. So whether that be the OS itself or sort of the user who's running the program. It also supports attested communication between the various different instances across different computers. The second building block we're going to use is speeds as our MPC library. What's kind of nice here is that we get to use our MPC library sort of as a black box. We chose to use speeds because it's really fast, but you could use any MPC circuit and you would kind of get the same guarantees. And then as our bulletin board, we're going to be using two different things, the Bitcoin network and the certificate transparency log. So you might say, and look at these sort of building blocks and say, wait a minute, you've got trusted hardware. If you've got trusted hardware, isn't this all trivial, right? Trusted hardware solves all security problems. And now this is sort of a very common thing that people have been saying recently, but it's really important to remember that, and a result this year, that trusted hardware alone cannot guarantee fairness, right? It's sort of susceptible to the exact same kinds of attacks that MPC was, which made this entire problem interesting, right? In order for different trusted hardware instances to communicate with each other, they have to go through a communication channel that might be secure in terms of the information traveling, but the malicious operators can simply drop messages. They can send an abort symbol instead of the actual message itself, right? So we can't get fairness just from trusted hardware. So our practical implementation is going to involve, once again, a bulletin board and a number of players. Our implementation looks like this, which is obviously a unnecessarily complicated diagram. So we're going to break it down into its various pieces. So the first one is this speed server and the speeds clients. Once again, we don't really have to care about the details of how the MPC itself works. We have to basically do one really important thing. We have to transform any given function f that we want to compute, and instead of computing just f of all the inputs, we want to compute the AS encryption of those inputs. Under what key, you might ask? We're going to be using a key that has various shares inputted from each of the players. You might also wonder why we're using AES here instead of public key cryptography, as we were doing before with real signatures. And that's because we really didn't want to put a public key crypto system into an MPC circuit. That seemed like a very good way to kill our efficiency very, very quickly. So instead, we had to sort of juggle some things around in order to get this to work, but we're able to do it using symmetric key crypto. When we're talking about efficiency in general and practicality, it's important to sort of look at the marginal cost of doing this, right? The sort of red parts of this graph was the overhead incurred by doing this AES encryption, where the blue parts are doing, this is a linear search over n elements, basically like an information retrieval type scheme, right? So this AES round can be very expensive if you're doing a very cheap function, but it's also constant sized, right? As you're doing more complicated circuits, the marginal cost of doing this AES encryption obviously shrinks. So I mentioned before these keys. Where do these keys come from? And that's where the second part, our second building block comes in, and this is where trusted hardware, Intel SGX. So each player in the MPC protocol is going to have an instance on their own computer. That instance is going to have two major roles. The first role is going to be generate a master key and distribute the shares among the various players, right? So because they have this communication channel between them that's guaranteed by SGX, they're able to sort of jointly agree on some KM, some key KM, and distribute it into each share, right? So each player will have access to one share, right, that the enclave will output upon request. But they won't, that enclave won't output the actual final key until the end of the protocol, right? When we implemented this, you'll notice that there's a couple of various pieces here. We had a master instance and a couple of minion instances. This was sort of just for ease of implementation. You could obviously have them sort of mutually contribute to the randomness of the master key, but because these are trusted execution environments, that's kind of a silly bunch of work to go through. Instead, we just have sort of the master instance determine a master key and distribute that to all the other players. The second role of the trusted execution environment is going to be sort of the final decryption phase, right? And in the witness encryption example, we were able to do this basically using the witness encryption itself, and that it was able to decrypt when the statement when the proof of public availability was given to it. In this case, we don't have that. So what we're going to do is basically the KM, the master K, is going to be living inside each trusted enclave, and in the final round, once, whether we're going to be using the Bitcoin network or the CT log, whatever it is, the bulletin board is going to sign this message, and we're going to have to verify that, that signature. So in the Bitcoin example, we're going to do the proof of work check a some number of blocks. In the CT signature example, we're going to basically verify the existence of some token within the CT log. We're also going to verify that the ciphertext that is up on the log is actually encrypted under the right key. So we're not just using any old AES, we're using an authenticated AES, right? And the last piece of our network is going to be sorry, the last piece of our implementation is going to be sort of the network aspect. This is the bulletin board aspect. In this example, in the drawing here, it's the Bitcoin network, and I'll talk a little bit more about CT in a moment. So the proof of work acts as our signature, and the release token is embedded into a transaction, right? So unlike a traditional signature where we say, it's has some, security parameter in how it has some parameter in terms of how secure it is. In the Bitcoin network, it's a little bit different, right? We don't have that same kind of security. Instead, we can make an economic argument. We can say, we're going to require a certain number of blocks at a certain difficulty level, and after that point, we're going to consider it signed. And that's a tunable metric. And unlike, if you roll your mind back to the beginning of the talk, when I was talking about fairness with penalties, where they had to sort of put up that money in advance, right? They had to put actual liquid cash into the protocol in order to guarantee its fairness. Here we can tune this to be as high of a metric as we want, right? And nobody has to put up any money. Nobody has to do anything. We can say we require 100 blocks with very high difficulty level, and that'll be totally fine, right? Another way of implementing a bulletin board is with certificate transparency. Roughly the way certificate transparency works is that you've got a giant Merkle tree. At the leaf of each of the tree are the various certificates that have been issued. So within our secure enclave, it's going to take sort of a path up to the Merkle root. So it's going to verify the leaf, take a path up to the Merkle root, and then it's given a signature over that Merkle root, right? So we're using traditional digital signatures here. It's worthwhile noting that this is pretty efficient in terms of our implementation, right? We don't have to worry about how much time it's going to take in order to do the verification of these two pieces, whether it be proof of work or certificate transparency. We're either doing a bunch of hash computations or we're verifying one signature. What is sort of a little bit slower here is the amount of time it takes for a transaction to actually be appended to the log, right? So we all know that it takes a little bit for a Bitcoin transaction to actually be confirmed and get pushed through. Similarly, in certificate transparency, we're not immediately guaranteed within a fraction of a second to have our new certificate be appended to the log. It takes, in reality, roughly about an hour from our observations, right? It would be possible if you need to speed that up to run using, for instance, a Bitcoin, or not a Bitcoin, sorry, a blockchain primitive that is much, much faster, right? Algorand being an example. So some conclusions and some open questions. One open question is it possible to weaken the type of witness encryption and still achieve the same result? As I mentioned before, we're using extractable witness encryption instead of traditional witness encryption. It would be nice if we were able to sort of pull back and use the traditional kind. Is it possible to further minimize the trust that we have in the bulletin board? Right? The bulletin board is actually a pretty strong primitive, and so it would be nice from a theoretical standpoint to see if we can minimize that trust assumption. And lastly, sort of as more conclusion, our proof is non-trivial. You should go check out the paper. I know in the description it seems the protocol seems rather straightforward, but the proof was not so easy. And there's going to be an ePrint version with certificate transparency implementation details coming soon as well. So with that, thank you very much.
Hi, Gabe. I'm Fan from Cornell. Great talk. And can you say a little bit about how to ensure that the trusted hardware is interacting with the correct blockchain instead of one that's simulated by the adversary?
Yeah. So implicitly here, we're doing we make some trust assumptions about the way that the trusted hardware is set up. So for instance, the certificate transparency version is a little bit clearer how you do this, right? Where there's a public key associated with the certificate transparency log that you're using, right? So you can hard code that key in. In the Bitcoin example, because our security is guaranteed economically, you don't have to hard code in the genesis block and then walk your way all the way up to the most recent time. You can actually just start at the block with the appropriate transaction and just append all the further blocks, right? Because it doesn't really matter which chain it's on as long as there's a minimum difficulty and a certain number of blocks. We're basically making the assumption that the adversary can't forge a large number of blocks, so it doesn't really matter where in the chain we slice that look for the appropriate transaction.
So you basically hard code the difficulty and require enough blocks.
Exactly right. Yeah. So the two things that are sort of we have to you have to sort of hard code the difficulty, which can be a little bit of a moving target, obviously, if the difficulty is actually changing in the live chain. But you sort of set a minimum difficulty, and you can appropriately set the number of blocks, and you'll get that guarantee.
Okay, thank you. Makes sense.
Hi. So when I look at the general multi-party computation, I can assume honest majority. Maybe it's depending upon how your adversary model is, but I saw when you are using this encryption keys, it seems like it's n out of n kind of situation. But it's not necessary, right? In your case, for example, if some node is non-rational, it's not rational and stop, then it's basically system is DOSed and you have to start again after removing that node.
Sure.
But it seems something which is solvable, right? Or
yeah. So I mean, I think there's a couple different pieces there in terms of the DOSability of the MPC protocol. It's important to say that we're not guaranteeing anything new about the MPC circuit itself. Right, so MPC is always DOSable, right? Because somebody can just drop out at any time and abort. And that won't necessarily change the fairness guarantee, because at that point, no player will receive the output. What we're trying to do is bootstrap onto the end of the MPC protocol, right? And at that point, any player can, once again, abort, but they're still not going to receive the output before they abort. And that's the fairness guarantee that we want to give. Does that make sense?
Hi, nice work. Two questions. One is that you are using the blockchain to ensure the fairness. So I wonder what's the delay, because you are using a blockchain, what's the delay when you're achieving the fairness in practice?
Sure. So in reality, it's a tunable parameter, basically, right? Depending on how much of a security guarantee, how much economic security you want to give yourself, you can wait longer or shorter. In reality, we know that it takes, if we consider like normal Bitcoin transactions, we're taking about an hour for a transaction to be confirmed.
Yes.
And so we have to wait for that amount of time. We might want to wait longer, or we might not care so much and wait shorter. But it's sort of a parameter of how much the parties want to guarantee their own security. In the CT model, we see it takes about an hour as well. But that's sort of an element of the blockchains, not the fair part. Right? So if you have an ideal bulletin board, it's going to sign automatically and give you back a signature. There are new blockchain protocols out there that are much, much faster, that use different sort of underlying protocols to move forward. I mentioned briefly Algorand is sort of an example where we would be able to cut down on that delay if we use a different building block for our bulletin boards.
Okay, another question is that what's the actual cost for you processing the output of the multi-party computation protocol? If the protocol has a very, very long output, would that cause a problem in practice?
Yeah, so I mean, the evaluation, the graph that I gave earlier, which showed sort of an overhead, was for basically doing, it does 2 rounds of AES. Two AES encryptions in order to get that marginal head. So obviously, if you've got a really, really long output, you're going to need to encrypt the whole thing. And so you'll incur sort of it'll be linear, obviously, in the length of your output.
So an immediate solution is that you use a random pad to pad your output. Is that doable with is that compatible with your protocol?
Yeah. So we, in the actual example, the test code that we ran, our output was 2 bits long. But we wanted to expand it, and so we padded out to a full block size before encrypting.
Okay, thank you.
Yeah. Any other questions? Great. Thank you.